Hi everyone, this video is on the fundamental theorem on finite abelian groups. We begin with an example. Let's suppose we have a group of order 45 and that we know it's isomorphic to some direct product of cyclic groups. The question is, what are the possibilities for those direct products? Well, we know that the only finite cyclic groups are the groups of modular integers, right? The z sub n's. And so G would have to be isomorphic to some direct product of zn's. And further, we know that the orders of these cyclic groups, they must multiply together to give the order of the group G, that is 45. So we know that n1 times n2 through nt multiplied together has to give 45. So that limits our possibilities. And so maybe the first thing we should think about is how to factor 45 into, a product. So we could just have 45 on its own. Or we could write 45 as 15 times 3. Or we could write it as 5 times 3 times 3. Or we could write it as 5 times 9. So those up to the order of the factors are the factorizations of 45. And so we would say then that the possibilities would then be Z45 and Z15, direct product with Z3, and Z5, direct product with Z3, and again with Z3, and then Z5, direct product with Z9. Okay, at this point, we might congratulate ourselves upon being done with this problem, but there is a little bit of a difficulty here, and that is that some of these groups are repeats of each other. For instance, because 5 and 9 are relatively prime, we know that the direct product of those two groups, Z5 and Z9, must be a cyclic group, right? Remember, this is something we talked about a little bit earlier of order 45. And so that means that Z5 cross Z9 is really the same as Z45. So these two groups here are duplicates. And similarly, Z5 cross Z3, because those are relatively prime, that is the same as the cyclic group Z15. So these two also are duplicates. So even though we've gotten all of the possibilities, we've sort of double counted them, and we don't want to do that. We want to just have we want to have all of our possibilities be non-isomorphic. So one thing we could do is just agree that we're only going to consider factorizations into prime powers. So that would eliminate this possibility here because 15 is not a prime power, and it would also eliminate Z45 because 45 is not a prime power. So if we just choose to look at cyclic groups whose orders are some prime power, then we're able to avoid duplication. Now, one thing you might be wondering is, well, what about these two groups that remain? How do we know that they're not isomorphic? Well, one thing you could see is that the bottom group, Z5 crosses Z9, has an element of order 9, whereas the one above it, Z5 cross Z3 cross Z3, does not have an element of order 9. Okay, now before we go on to the next slide, I want to point out something about our prime factorization of 45. So 45 is written as 5 to the first times 3 squared. Now, in terms of counting these number of possibilities, the exponents that we find in the prime factorization are going to be important, right? So the 1 on the 5 tells us really that there's, if you want to, that there's really only Z5 as a possibility there. However, the 2, which is the exponent on the 3, tells us that we could write, our 3 squared as 9, and this would sort of correspond to Z9, I guess. Or we could write it as 3 times 3. Which would then correspond to this Z3 cross Z3. So in some sense, for each exponent, the number of ways that we can take that exponent and express it as a sum of integers is going to play a role in the number of possibilities that we get. Okay, if we were to do several more examples like we did on the previous slide, we'd begin to make some observations about those examples. So if G is a finite group that happens to be isomorphic to a direct product of finite cyclic groups, then we know, as we pointed out on the previous slide, that that group would have to be isomorphic to some direct product of Zn's, because the Zn's are the only finite cyclic groups. And furthermore, the n's in question would need to multiply together to give the order of the group G. Further, to avoid duplication, as we saw in the previous slide, we would want each one of these orders of the finite cyclic groups to be some prime power. All right, and then another observation is that if we take our group order and we write its prime factorization, where we gather together all the prime powers in the factorization of G, then if we want to count the number of non-isomorphic possibilities, we obtain this number here. So what is that number? Well, pi is what's called the partition function. So it's going to take a number k, and it's going to count the number of partitions of k, meaning that's going to be the number of ways that you can write k as a sum of positive integers. So what we want to do is take all of these exponents, sort of as we pointed out on the previous slide. We're going to compute the partition function for each one of those exponents, and then we're going to multiply the results. And that will give us the number of non-isomorphic possibilities for G. So if we go back, say, to if we look at the example on the previous slide, right, remember there G was of order 45, which we could write as 3 squared times 5 to the first, right? So the number of possibilities here according to our little formula in Roman number 2 would be the partition function of 2 times the partition function of 1. Now, we need to compute what those things are. Well, how many ways can I write 2 as a sum of positive integers? Well, I could just write 2 as 2, or I could write 2 as 1 plus 1. So there are two ways to write the number 2 as a sum of positive integers. So pi of 2 is equal to 2. Likewise, if we look at 1, there's only one way to write the number 1. So the partition function of 1 is just 1 itself. So we multiply 2 times 1 and we get 2 for the number of possibilities. And you might remember from the previous slide that that's exactly the number of possibilities that we obtained, right? We had Z5 cross Z9 and Z5 cross Z3 cross Z3. To help us get a better feel for this, let's try another example, just like we did on the first slide. So here, however, our finite group is of order 144. And again, as on the first slide, we're going to assume that this group is isomorphic to a direct product of cyclic groups. And we want to write down the possibilities, just as we did on the first slide. So here, let's make use of the observations that we made on the previous slide. Let's first compute the number of possibilities before we try to write them all down. So we know that the order of our group, G, is 144, and we can factor that into primes as 3 squared times 2 to the 4th. Okay, now remember that we want to compute the number of possibilities, we want to focus now on these exponents, 2 and 4. So the number of possibilities is the partition function of 2 times the partition function of 4. Now we already saw in the previous slide that there are only 2 ways to write 2 as a sum of positive integers. How many ways are there to write 4 as a sum of positive integers? Well, you could have just 4 by itself, or you could have 3 plus 1, or you could have 2 plus 2, or you could have 2 plus 1 plus 1, or you could just have 4 ones. So there are 5 ways to write 4 as a sum of positive integers. So the partition function applied to 4 gives 5 as an output. And so the total number of possible non-isomorphic groups of this type is 10. Okay, now that we have the number of possibilities, let's try to write them down. Okay, so let's suppose that the first factor is Z9. Then the second factor has to have order 16. So we could first put Z16 here. 16 is 2 to the 4th power. Or we could write Z9 cross Z8 cross Z2. There, that group, the 8 is 2 cubed, the 2 is 2 to the 1st. So let's keep going. So our first factor continues to be Z9, and our next factors need to have orders that multiply together to give 16. So the next thing that we might do is Z4 cross Z4. 4 is 2 squared. So each of the 4s is a 2 squared. So that corresponds to that partition of 4. Now let's keep going. We have Z9. And again, we want a product of groups whose order, the product of the orders of the individual groups gives 16. So what if I did this? I could do Z4 cross Z2 cross Z2. So the 4 is 2 squared. Each one of the 2's is 2 to the first. And then finally we have this one. So in that one, all of the groups to the right of Z9, their orders are 2 to the first, 2 to the first, 2 to the first, and 2 to the first. So that accounts for that partition of 4. Now, we're not quite done because we've only listed 5 possibilities. And so where are the other 5? Well, they come from, instead of writing Z9, which is 3 squared, we could write this as Z3 cross Z3, where it's of order 3 to the first and then 3 to the first. So we just sort of repeat these. All of the first 5 that we had, except every place we see a Z9, we replace it with Z3 cross Z3. Right? Well, we'll just keep doing this. So Z3 cross Z3, cross C4 cross Z4. And now we're over to this one here. So Z4 cross Z2 cross Z2. And now I believe we only have one more to do. It's Z3 cross Z3 cross a whole bunch of Z2s. Okay, and there are the 10 possibilities. In the previous slides, we've been discussing what to do when you know that your group is finite and that it's a direct product of cyclic groups. So the question then is, which groups are like that? Well, we have this theorem, it's a very important theorem, that says that any finite abelian group whatsoever is going to be isomorphic to some direct product of cyclic groups of prime power order. So what that means is that the sort of analysis that we've been doing on the previous slides could be done really to any finite abelian group. So to emphasize that, let's do this example where we're going to classify all abelian groups of order 900. So the groups are abelian, and if we apply this theorem, which is known, by the way, as the fundamental theorem on finite abelian groups, if we apply that theorem, we know that any abelian group of order 900 must be isomorphic to a direct product of cyclic groups. And so what we're going to do essentially is exactly what we've done on the previous slides, right? So we know that whatever our group is of order 900, we can write it as a product of prime powers. So it turns out to be 2 squared times 3 squared times 5 squared. And therefore, the number of possibilities is going to be this product of partitions, right? Remember, we focus on the exponents. And so we're going to think about how many ways we can take 2 and write it as a sum of positive integers. And we recall from previous slides that pi of 2 is just 2 itself. So we know that there are 8 abelian groups of order 900. And now we need to write them out. So we could start like this. We could do Z4 cross Z9 cross Z25. So there it's, each prime squared, right? So 2 squared, 3 squared, and 5 squared. So now we can just keep the first 2 factors as they were. But now, if we write 2 as 1 plus 1, as exponents on 5, that gives us just Z5. 5 to the first, cross 5 to the first. Sorry, and this should not be an equals. This should be a comma. They are not the same. They are non-isomorphic groups. Okay, so we've handled there all of the possible partitions of 2 as considered as an exponent of 5. So why don't we now go here. Okay. Right, so we've written 4 of them now, and the other 4 come from writing for the other 4, just replace in all of these 4 Z4 by Z2 cross Z2. In the remaining slides, we're going to sketch a proof of the fundamental theorem on finite abelian groups. Some of the results that we will see along the way are interesting and important in their own right, including this first lemma, lemma 1. So this lemma tells us about a scenario where we have a group G with subgroups A and B, and it gives us conditions under which we'll know that G is a direct product of A and B. So those conditions are that we would like A and B to be normal in G. We would like A times B to equal G. That means that every group element can be expressed as something in A times something in B. And then finally, we want the intersection of A and B to be the identity. So if those things are in place, then we'll know that G is isomorphic to the direct product of A and B. Okay, now to prove the theorem, we start with some preliminary calculations that will be useful later on. So we have A and A1 in capital A, B and B1 in capital B. If it so happens that A times B is equal to A1 times B1, then we can manipulate that equation to get A1 inverse times A equals B1 times B inverse. Now the thing here on the left, that's in A. The thing on the right, that's in B. The two quantities are equal, and so they must both lie in A intersect B. But remember, A intersect B is the identity, and so that tells us, for instance, that A inverse A is equal to the identity, and if you move the A1 inverse over to the other side, then you get A equals A1. Likewise, you can take this equation here and move the B over to the other side, and you get B equals B1. So essentially, this is a statement about uniqueness, right? It means that if you have a group element that's expressed as something in A times something in B, then that representation is a unique representation. Okay, now the second calculation is going to tell us that everything in A commutes with everything in B and vice versa. And how do we see that? Well, if we look at this product, AB times A inverse times B inverse, if you focus on this first, the product of the first three objects there, A times B times A inverse. Remember, B is a normal subgroup of G, and so that means that A times B times A inverse, that's again in B. And so when I multiply that thing times B inverse, I again get something in B. So I know that that product of stuff is in B. On the other hand, you could, wipe this out here, and now instead focus on the product of the last three things. Well, that's B times A inverse times B inverse. Well, A is normal in G, and that means that B times A inverse times B inverse is once again lying in capital A. And then if I multiply by little a on the left, I get something again that's in capital A. So this weird looking product lies in both A and in B. And that means that because the intersection is trivial, it means that this product is equal to the identity. And then if you move the inverses over to the other side, you get this result. Okay, so we really relied on the normality of A and B in order to establish this result. Okay, now remember, the lemma is telling us that the group G is isomorphic to A cross B. And in order to establish that, we're going to need an isomorphism. So that means we need a function that joins A cross B to G. So let's define a function phi here that will eat elements in A cross B and spit out elements in G. And the way it's going to do it is just going to take an ordered pair, little a comma little b, and multiply them together to give an element of G. So phi essentially is just a multiplication function. Takes something in A, something in B, and multiplies them together. Right, so what do we need to know about this phi? If it's going to be an isomorphism, it needs to be both one-to-one and onto, and it needs to preserve the operation. So we know it's onto by hypothesis. That's because, G is equal to A times B, meaning that everything, if you pick anything whatsoever in G, you can express it as a product, as some product, little a times little b. So next, let's show it's one-to-one. Let's suppose we have phi of A comma B equaling phi of A1 comma B1. That says that A times B equals A1 times B1. But remember, item 1 then tells us that A has to be A1 and B has to be B1. And that means that these two ordered pairs must have been the same to begin with. So that means that the function phi is one-to-one. And then using item 2 up here, we can show that phi is a homomorphism, right? So we take phi of a product. Well, how do we do that? That's phi of AC comma BD. Phi takes those two things and multiplies them together. Now remember that C is in A and B, little b is in capital B. And so I can take this product by item 2 above and reverse the order. But then once we have that, we see that that's phi of AB times phi of CD. Therefore, phi of the product was the product of the phis, and so this function phi is a homomorphism. So if you put all of that stuff together, the onto, the one-to-one, and the homomorphism, you get that phi is an isomorphism, which establishes that G is isomorphic to A cross B. We now, in this slide, move a bit closer to the fundamental theorem on finite abelian groups. So we begin with a definition. So we start with a group G and a positive integer k. So we're going to define this set G of k to be all of the things in G whose kth power gives us the identity. Now, this thing is going to be a subgroup of G. Certainly when G is abelian. In fact, it might not be a bad exercise to just pause the video right now and see if you can verify that if G is an abelian group, then this object, G of k, is going to be a subgroup of G. Okay, so given that we know what this G of k gadget is, we now move on to our second lemma. So it says, suppose G is abelian and its order is Mn, where M and N are relatively prime, then G is isomorphic to the direct product of G of M and G of N. So this looks a lot like the result of lemma 1. And in fact, the whole goal here is to apply lemma 1, where G of M and G of N are going to play the roles of A and B in the previous lemma. So first of all, these groups, these subgroups, G of M and G of N, are normal subgroups of G, and that's because our group G is abelian, and so every subgroup of an abelian group is normal, right? So the reason here in this sentence, the reason G of M and G of N are normal is because G is abelian. Now, because M and N are relatively prime, there's a fact about integer divisibility that we talked about maybe months ago. It says that whenever M and N are relatively prime, you can find other integers R and S where Rn plus Sm is equal to 1. Okay? And that means if you select anything in G whatsoever, say x, you can write it as x to the first, but 1 is Rn plus Sm, and then you can rewrite it as x to the Rn times x to the Sm. And further, this x to the Rn is in G of M, and x to the Sm is in G of N. So that would mean that anything in G, this x, right, we wrote x as something in G of M times something in G of N. And so we have that G is equal to G of M times G of N. So let's take a moment to just see if we believe that x to the Rn is in G of M. Okay, so what does that mean? Well, I need to take x to the Rn and I want to raise it to the mth power, and my hope is that I get the identity, right? So I can write that essentially as x to the mn to the rth power. But remember, mn is the order of the group. And we had a result a little while back that says that if in a finite group, if you have an element and you raise it to the order of the group, then you get the identity. So that's just the identity. All right, so we've shown that these two groups, Gm and Gn, are normal. We've shown that the larger group G is the product of G of M and G of N. And then the final thing we need to do in order to apply lemma 1 is show that the intersection of the two is trivial. So let's pick something, some x in the intersection. Then we play sort of the same game we played before. So x to the first is x to the Rn plus Sm. You break it up like this. If x is in Gn, right, then this is the identity. And because x is in Gm, this is the identity. And so that means that everything in the intersection, anything in the intersection must just be the identity. So now the way is clear to apply lemma 1. We know that we have our two groups that are normal, whose product yields the whole group G and whose intersection is trivial. So G is isomorphic to the direct product of Gm and Gn. So in the course of our discussion, which might have been rather lengthy, of lemmas 1 and 2, we might have forgotten what the fundamental theorem on finite abelian groups is. So here it is again. It tells us that every finite abelian group is isomorphic to a direct product of cyclic groups of prime power order, and that product is unique up to isomorphism. So colloquially, it says, well, if you have any finite abelian group, it's just some product of Zn's where the n's are all prime powers of some sort. So how do we prove it? Well, start with an abelian group G of order n, and then write the prime factorization of n, where we go into prime powers. So here, all of the P1 through PT, so these primes, are distinct primes. Then, if you apply lemma 2 repeatedly, what you have is that our group G has to be isomorphic to this direct product, G of P1 to the R1 up through G of PT to the RT. And so really the only thing that remains is to show that each of these guys here that were defined on the previous slide, that each one of them is a direct product of cyclic groups of pi power order. So to finish the proof of the fundamental theorem on finite abelian groups, we need a lemma like lemma 3 here. It says that if P is prime and R is a positive integer, and we have a finite abelian group capital G, where x to the P to the R is the identity for all x in G, then G is isomorphic to a direct product of cyclic groups of P power order. So how does this help us go from the bottom of the previous slide to a proof of the theorem? Well, this lemma 3 is going to apply to all of these G of, P sub I to the R sub I's on the previous slide. Right, and so if all of those are products of cyclic groups of P power order, then that finishes the proof of the theorem. Okay, so it's claimed here that we're proving the theorem, but really this is just going to be a sketch of the proof of the theorem. For the complete proof with full details, I recommend that you read it in its entirety in our text. So this is a proof by induction, which we haven't seen for a little while. So we're going to induct on the order of G. So we claim that the result is true when the order of G is 1. That is when G is the identity group. So if G is just the trivial group consisting of the identity, then that is indeed a cyclic group. And its order is order 1, which is P to the 0. So it is of P power order. Okay, so we know the result is true when the order of the group is 1. So now let's suppose we have our group and its order is bigger than 1, and we're going to assume that the statement is true for all groups of smaller order. So we pick an x in G with x not equal to the identity and let A be the cyclic subgroup generated by x. So I know that x to the p to the r is the identity. That's true for all x in our group. And so the order of x has to divide p to the r. And that means that because the only divisors of p to the r are powers of p, we know that A is a cyclic group of p power order. Now, if that's all of G, then we're completely done, but it might not be all of G. So now what we would like to do is to find a subgroup B of G where all of these conditions hold, that A intersect B is the identity, and A times B equals G. Because if that were true, then you could imply the lemma 1 together with the induction hypothesis on B to get the desired direct product. Remember, B would then have strictly smaller order than the order of G. And it, according to the induction hypothesis, would then be a direct product of these cyclic groups of p power order. And then if you put it together with A, which we already know is a cyclic group of p power order, you would get that G is a direct product of these cyclic groups of p power order. So then the main thing is, well, how do we find this B? So the place to start is to look at the quotient group G mod A. So we're going to look at the cosets of A and G. And it has the right size, right? It has the correct size that we want. But G mod A is not necessarily, it's not a subgroup of G. And so what we would have to do to form a subgroup of G is to take this, is to look at some particular coset representatives, right? So, G mod A is going to be some cosets. In fact, all the cosets of A in G. And what you want to do is sort of select representatives of these cosets in a good way to form this subgroup B. So once you have done that, then you will have proved the theorem.